jet which is striking an unsymmetrical moving curved vane tangentially at one of the tips. So this is the inlet tip and this will be the outlet tip. Now the vane is moving in the horizontal direction with velocity u, but the jet is striking with in some other directions. So here the jet issues from the nozzle at an angle alpha. So but this is the velocity with which the jet doesn't strike the vane, because when the jet is about to strike, the vane would have moved with velocity u. Therefore, the velocity with which the jet is striking is nothing but the relative velocity of the jet, which is represented as VR. We know that for no shock, the jet has to enter tangentially. So see, VR is in the tangential direction, therefore VR has to be in the tangential direction. So the jet enters with velocity VR and comes out with velocity VR1. VR1 is generally 0.9 times VR or 0.85 times VR, depending upon the loss of energy that takes place when the jet is gliding over the inner surface. If no losses are given, so then VR1 can be taken equal to VR. Here, in this case, the velocity v is also known as the absolute velocity, which is a resultant of u and vr, line joining from tail to tip, where u is in the direction of motion of the vane, where vr is in the tangential directions. So this angle alpha is the angle of the jet which issues from the nozzle. Now you know that if you take the angle of this tangent with respect to the direction of motion of vane, that is known as theta, which is called as a vane angle at the inlet, whereas if you take the angle of the tangent with respect to the direction of motion of the vane is known as phi, which is vane angle at the outlet. If theta is equal to phi, then this vane becomes symmetrical. We also have the various terms like Vf and Vw. So Vf is the component of the velocity v perpendicular to the direction of motion of the vane. So which is Vf, which is given by v sine alpha, and is known as the velocity of flow at the inlet. The component of velocity v in the direction of the motion of the vane or parallel to the direction of motion of the vane is known as velocity of whirl. So Vw, okay, is represented by Vw. So similarly, we have Vr1, like, which is the relative velocity at outlet. So V1 is again, so by the time the jet comes out, the vane would have moved with velocity u. So therefore, so if a person moving with the vane will observe that, so he will observe that the the jet issues in the tangential directions, whereas the person outside will observe that the jet will be coming with velocity v1. So v1 is the resultant of vr1 and u. So v1 is nothing but the absolute velocity at the outlet, where the component of v1 in the horizontal direction is vw1, which is known as velocity of whirl, and vf1 is in the perpendicular direction to the motion of the vane, which is vf1. So this is known as velocity of flow at outlet. Vw1 is known as velocity of whirl at outlet. So here the jet strikes with velocity Vr. The jet strikes with velocity Vr. So now we are required to find the force exerted in the direction of motion of the vane. So if it strikes with velocity Vr, the component in the x direction is Vr cos theta. Vr cos theta. So this is Vr cos theta. If Vr cos theta is nothing but Vw minus u. Now the jet comes out with velocity Vr1. So therefore the component is at the outlet is Vr1 cos phi. If beta is less than 90 degrees, then we have this case where from here to here this is Vr1 cos phi, which is, that is because it is okay, it is in this the component is in this direction, therefore it is minus Vr1 cos phi. but VR1 cos phi is u plus VW1. So now we know that force exerted is mass per second multiplied by initial velocity, which is Vr cos theta. Final velocity is minus Vr1 cos phi. So depending upon the beta angle, so the value of Vr1 cos phi changes, which will be going in the next slide. Here we have, in this case, so if Vr1 is the component of the velocity, so this is Vr1 cos phi. So minus Vr1 cos phi. So what is Vr1 cos phi? It is u plus Vw1. So this is the case where beta is less than 90 degree. So Vw1 is, so this is Vr1 cos phi minus u. So there is also a case when beta becomes 90 degree. That means here the V1 will be in this at 90 degrees. So V1 will be equal to Vf1, where Vw1 will be equal to 0. But Vr1 cos phi is equal to, that is minus Vr1 cos phi is equal to u. That is minus u. In this case, if u is greater than Vr1 cos phi, if u is greater than Vr1 cos phi, then we get that the jet leaves, okay, in this direction where beta is obtuse angle. So therefore we have, if this is Vr1, so minus Vr1 cos phi is this. So Vr1 cos phi is nothing but u minus Vw1, u minus Vw1. So this will be used in the derivation. So that is what we have considered a jet of cross section area A and velocity V, which is striking the vane tangentially. So the vane is also moving, so the effective velocity with which the jet will strike will be the relative velocity, that is Vr. So that is actually Vr is the actual velocity with which the jet enters the vane at the inlet. So after striking, it comes out with velocity Vr1 at the. So these are various terms that I had explained earlier in the sketch. And these are also again the various terms like Vf, Vw, Vf1 and Vw1, which I had already explained. So now you know that the mass of fluid striking the beam per second is that is density into discharge. So rho A into Vr. So component of velocity Vr at inlet in the direction of motion of the vane is Vr cos theta. So you know that Vr cos theta is Vw minus u. Okay, the component of velocity Vr1 at outlet in the direction of motion of the vane is minus Vr1 cos phi. So if beta is less than 90 degree, I told you that Vr1 cos phi is u plus Vw1. So now you apply impulse momentum equation in the direction of motion of the vane. So force exerted on the vane in the direction of motion of the vane is mass per second into initial velocity minus final velocity. So mass per second is rho a Vr. Initial velocity is Vw minus u. Minus is for the change, so final velocity is minus of u plus Vw1. So Vw1 minus u, minus of minus is plus, so therefore these two cancels out, so we are left with rho a Vr to Vw plus Vw1. Similarly, when beta is equal to 90 degrees, then the component of velocity Vr1 at the outlet is minus Vr1 cos phi. We know that Vw1 will be 0, so therefore it is minus u. So substitute the, again in force equations, the force is nothing but mass per second into initial velocity minus the final velocity. So this gets cancelled out, so you are left with Vw. When beta is greater than 90 degrees, then again we can find the component of velocity Vr1 at the outlet. So that is minus Vr1 cos phi. So that is given by which I had already discussed, which is minus of u minus Vw1. Substitute, that is initial velocity minus final velocity. So minus of minus plus. So therefore we get, this cancels out, so we get Vw minus Vw1. So hence in general we can write as force as rho a Vr Vw plus or minus Vw1. So if beta is less than 90 degrees, use plus sign. If beta is greater than 90 degree, use minus sign. If beta is equal to 90 degrees, then Vw1 will be equal to 0. So likewise, after finding out the forces, so work done per second, because force is in the x direction, u is in the x direction, so it is simply work done is per second is F into u. So taking the force equation and multiplying by u, will get the work done, which is output. Input is same as kinetic energy per second, so therefore half mass per second into V square. So half rho AV into V square. So therefore efficiency can be calculated as output by input. So that is the equation that we are going to use in the problems. So understanding this, how to write velocity triangles both at inlet and outlet, we can solve. Now coming to the first problem, a jet of water of diameter 50 millimeters. So D is 50 millimeters. So having a velocity that is V is 25 meter per second, moving with a velocity that is strikes a curved vane which is moving with a velocity of 10 meter per second. So U is 10. The jet makes an angle. So that means with issues from the nozzle. So that was angle alpha is given 10 degrees, and the jet leaves the vane at an angle of 120 degree to the direction of motion. So the direction of the V1 is given, so which is 120 degrees. So beta can be calculated as 180 minus 120, 60 degrees. So vane angles at inlet and outlet is to be calculated, work done per second, and efficiency has to be calculated. So now this is the figure where the jet issues at an angle alpha, so that is here. So by the time the jet strikes, the vane would have moved with velocity u. So the jet actually striking with velocity vr, so which is at an angle theta. So this is the tangential direction to the vane. So the component of v is vw, vertical component is vf. So now knowing the diameter of the jet, so you can find the area, so which comes to 1.9625 into 10 raised to minus 3 meters square. So now we can find from this triangle, so VF is nothing but, okay, V sine alpha. So therefore 25 into sine 10 gives 4.34 meter per second. We can also find the component, horizontal component of V, which is given by V cos alpha. So knowing V and knowing alpha, we can calculate VW, which is 24.62. Now take this triangle, and you can calculate the vane angle at inlet. So tan theta is nothing but VF, the perpendicular by base. So this distance is VW minus U. So therefore VF by VW minus U. Substitute the values of VF, VW and U, so we'll get theta. So the vane angle at inlet is 17.3 degrees. And also it is required to find out VR. So we can again take the same triangle, that is sin theta is VF by VR. So therefore VR can be calculated, which is given by VF by sin theta. So VF is known, which is 4.34, and divided by sin 17.3, which gives to 14.59 meter per second. So nothing is mentioned about the losses, so we can assume VR1 equal to VR, which is 14.59 meter per second. So now assuming this VR1 is equal to VR, now we can draw the sketch. So here it is given that now it moves out in the tangential direction, that is VR1. So now, so by the time the jet comes out, the vane would have moved with some velocity u. So we know that the jet, okay, comes out or leaves the vane at an angle, okay, 120 degrees. So that means this is fixed with the direction of motion. So this is the direction of motion, so this direction is fixed. So now since this is 120 degrees, okay, we have, so this angle is 120 degrees, so this beta will be now 60 degree. So therefore beta is less than 90 degree. So this total is 180. So therefore this angle is known, which is 120 degrees. So this angle is phi. Okay, so the tangent that makes the direction of motion of the vane is phi. So therefore this is phi. So just name this angle as something like phi 1. So now we can apply, or you can take this triangle and apply sine rule. So now VR1 by sine 120 is equal to U by sine phi 1. So VR1 is known, okay, U is known, so phi 1 can be calculated. So phi 1 is calculated as 36.4. So you know that phi plus 120 plus phi 1 should be equal to 180 degree. So therefore phi can be calculated, which comes to 23.59 degrees. So this is nothing but the vane angle at the outlet. So coming to VW1, so VW1 is nothing but VR1 cos phi minus U. Okay, so which is, so you know VR1, so you know 5 angle, so hence VW1 can be calculated, which is 3.37 meter per second. So since beta is less than 90 degree, we are using plus sign for the force exerted. So it is mass per second into change in velocity. So therefore it is VW plus, because we are using plus sign because beta is less than 90 degrees. Knowing rho, which is density of water, 1000 kg per meter cube. Area is known, VR is known. So VW is known, VW1 is known. Hence the force exerted can be calculated. It comes to 801.43 newtons. So work done per second is force into velocity. So therefore velocity of the vane, so multiplying by 10, so gives 8014.3 Newton meter per second. Similarly, the kinetic energy per second can be calculated, which is the entire mass of fluid that issues from the nozzle is half mass per second into V square. So half into rho AV into V square. So half into 1000, area is known, so velocity is known, so hence the kinetic energy per second can be calculated. So therefore efficiency is nothing but output by input into 100. So the output is known, which is work done per second, 8014.3 divided by the input, which is 15332.03 into 100, which comes to 52.3 percentage. The second problem is that here in the previous problem the jet was living at an angle something like 120 degrees. Here it is living the vane at an angle of 90 degrees. So very simple problem as compared to the previous problem. So a jet of water of diameter 75 millimeters having a velocity of 30 meter per second strikes a curved vane which is moving with velocity 15 meters per second. So D is 75 millimeters. So capital V is 30 meter per second, whereas the velocity of the vane, that is U, is 15 meter per second. So jet makes an angle, somebody alpha is 30 degrees. So then here beta dash is 90 degrees, so therefore beta has to be 90 degrees. So we have to find the vane angles at inlet and outlet, that is theta and phi, work done per second, and efficiency. So knowing the diameter, we can calculate the area. So now the jet issues at an angle alpha. By the time the jet strikes the vane would have moved with velocity u. So therefore the jet strikes with velocity vr, which is in the tangential direction. So this angle is theta. So alpha is given. So V is known, U is known, alpha is known. So we are able to calculate VF, VW, and then theta. So as usual, so VF is V sin alpha, VW is V cos alpha. So then using tan theta equals VF by VW minus U. So that's what the sketch is again repeated here. So therefore VF is V sin alpha, which gives us 30 sin 30, which is 15 meter per second. So VW is V cos alpha, which is given as 30 cos 30, which is 25.98. So using this triangle, we can calculate tan theta, which is VF by VW minus U. So therefore theta is 53.8 degrees. So also from the same triangle, you can calculate sin theta equals VF by VR. Therefore VR can be calculated as 18.6 meter per second. We can again assume VR1 equals VR, which is again 18.6 meter per second. So now it is said that it comes out with velocity. This has to be VR1. Okay, so the VR1 is equal to VR. So therefore it's okay if you write even VR. So VR1 is equal to VR. So it comes out with velocity VR1. So since it comes out here, like the jet comes out with an angle 90 degrees. Okay, this is always in the tangential direction. So this comes out 90 degrees. So beta is 90 degree. So we know that V1, in this case V1 is equal to VF1. So VW1 is 0. VW1 is 0. So U is nothing but VR1 cos phi. Okay, so now we can apply sine rule and find out. So u by, so for example this is 90 degree, so u by sine phi 1 is equal to vr by sine 90. So this is 90 degrees. So therefore phi 1 can be calculated as 53.75. We know that phi plus phi 1 plus 90 is equal to 180 degree. So therefore the angle of the vane at the outlet can be calculated as 36.25. So we know that for beta is equal to 90 degree, VW1 is 0. So VW1, so this has to be VW1. So VW1 is 0. So therefore rho AVR into VW So plus or minus VW1, that is 0. So therefore we can calculate the force exerted, which is 2133.74 newtons. So work done per second can be calculated as force into U. So therefore U is the velocity of the vane. So therefore the work done per second is calculated. Similarly, kinetic energy per second is half mass per second into V square. So half into 1000 into multiplied by the area into the velocity cube. So that gives kinetic energy as 59610.6 Newton meter per second. Efficiency is nothing but work done per second divided by kinetic energy per second into 100. That comes to 53.7%. So coming to the third problem, the first problem we had taken beta dash as 120 degree. Second problem it was 90 degree. So now we take a case where beta dash is 60 degree. Therefore beta will become 120 degree, which that means it is obtuse angle, where we are using now for force here rho a VR VW minus VW1. So that's the change. So to show that change, so I've taken this problem. So now jet of diameter 50 millimeters is having velocity. So V is 20 meter per second. It strikes the vane which is moving with velocity 10 meter per second. Jet issues at an angle that is alpha 15 degrees. So now beta dash is given as 60 degrees. So therefore beta is 120 degrees. Same thing, we have to find vane angles at inlet and outlet, work done per second, and efficiency. So this is the problem where knowing the diameters we can calculate the area. So now this is V. So the jet issues from the nozzle at an angle alpha. So by the time the jet strikes, the vane would have moved with velocity u. So therefore the velocity with which it strikes is Vr, which is in the tangential direction to the vane. So this angle is theta. So now we can, using V and alpha, we can calculate Vf, which is V sin alpha. Vw is V cos alpha. So therefore tan theta is Vf by Vw minus u, which is shown in the next slide. So knowing the area, so now we can calculate Vf, which is V sin alpha, which is 20 sin 15, 5.18 meter per second. Vw is V cos alpha, which is 20 cos 15, so therefore 19.32 meter per second. So using this triangle, so we can calculate, okay, Vr, that is tan theta. Sin theta is Vf by Vr. So therefore Vr is Vf by sin theta. So which comes to 10.65 meter per second. So since losses are not given, so we can assume VR1 equals VR, which is 10.65 meter. Now it is given that, so the jet, so this VR1 is in the tangential directions. Okay, VR1 is the effective relative velocity at the outlet, but it is given that the jet leaves at 60 degree with the direction of motion of the vane. So that's the reason why the beta, so this is 60 degrees, so therefore beta becomes 120 degrees. So therefore jet here, because of obtuse angle, so here it is, we have to use in the force equation as Vw minus Vw1. Okay, so if this is 120 degrees, so this angle is 60 degrees. Now by sine rule, so let this, so this angle is phi. Okay, this is 60 degree. So let this, because you have to take this entire triangle, so this angle will become phi 1. So we are applying sine rule to this triangle. Okay, to this triangle. So therefore u, which is u. So in this case we find that since beta is obtuse angle, here we find that u is greater than Vr1 cos phi. Okay, so now u by sine phi 1 equals Vr1 by sine 60. So therefore u is known. So phi 1 is not known, it is to be calculated. Vr1 is known from the previous calculation, 10.65 by sine 60, where phi 1 is 54.41. So we know that phi plus phi 1 plus 60 is 180 degrees. So therefore phi can be calculated, which is the angle of the vane at the outlet, which is comes to 65.6. Now we can calculate here again the velocity triangle is written. So here from this the component of V1 is Vw1 horizontal and vertical is Vf1. We know that this is Vw1, so which is u minus Vr1 cos phi. So therefore u is known, Vr1 is known, and phi is known, so hence Vw1 can be calculated. Now since beta is more than 90 degrees, we are using minus sign. So therefore rho AVR into VW minus VW1, which is density 1000 kg per meter cube. A is known, so VR is known, so VW is 19.32, VW1 is 5.6, so which comes to 286.76 newtons. So work done is again force into velocity. So multiplying by the velocity 10 meter per second gives 2867.6 Newton meter per second. So now kinetic energy is half mass per second into V square. So again calculated half into 1000, substitute area and velocity, so which gives 7850 Newton meter per second. So efficiency is work done per second by kinetic energy per second into 100, which comes to 36.5%. So this is a particular case where the jet, okay, the jet and the vane are in the same direction at the inlet. So that's why it is given. It's a very important problem, which is moving with velocity 10 meter per second in the direction of the jet. So this statement becomes very important in this problem. So diameter is given 50 millimeters, velocity V is 20 meter per second, and velocity of the vane is 10 meter per second, but the vane is moving in the direction of the jet at the inlet, and at the outlet the jet leaves at an angle 60 degree to the direction of motion of the vane and outlet. So now you can find the force exerted, work done per second, and efficiency. So this diagram is given so very clearly here. So now the vane direction is horizontal, so here, so the and the jet direction is also horizontal, they are moving in the same direction. So that's the reason why. So by that the jet strikes, so the vane would have moved some velocity, therefore here this becomes VR. So since they are same direction, so we have VR as V minus U. Here alpha is also 0 and theta is 0. So the okay, the nozzle issues the jet in the same direction. So therefore theta is 0 and alpha is 0. In this case, so this is the incoming direction, this is the outgoing direction, and this will be the deflection angle. So this will be the deflection angle. Now it is given that the jet leaves at 60 degrees. So jet leaves, so this is the tangent direction, so VR1 direction. So this, if this angle is phi, so this angle will be phi. So since this is 60 degree given, so beta will be 120 degrees. So obtuse angle there is greater than 90 degrees. So it is in the force equation we get VW minus VW1. So since this is 120 degrees, so this will be 60 degrees. Now knowing diameter, we can calculate the area. So velocity is known, U is known, so beta dash is known, so beta can be calculated. So in this case it's a linear diagram. So alpha is 0, theta is 0, so VR becomes V minus U. So and also we know that VW is always V cos alpha. Alpha is 0, so cos 0 is 1, so VW will be equal to V, which is 20 meter per second. We can also assume that since there is no loss, so VR1 is equal to VR, which is 10 meter per second. Now at the outlet the jet leaves at 60 degrees, so this is the VR1 directions now, and the component of V1 is horizontal component is VW1 and this is VF1. So now we are required to find the angle phi. So take this completed triangle. If this is 60 degree, if this is phi, so take this angle as something like phi 1. So therefore by sine rule we can write VR1 by sine 60 should be equal to U by sine phi 1. From this you can calculate phi 1, so which is 60 degree. So phi plus phi 1 plus 60 is equal to, so 180 degree. So slight mistake here, so it is 180 degree. So therefore phi is 180 minus 60, which is 1, okay, total. So phi plus phi 1 is plus 60 is 180 degree, so therefore it has to come as 120. So 120 minus 60 is 60 degrees, so that's what it will wrongly written here. So it will be 120 minus 60, okay, so therefore phi should be 60 degrees. Now we know that to calculate VW1, so VW1 is U minus VR1 cos phi, so therefore it is 10 minus 10 cos 60, which is 5 meter per second. So force is rho AVR into VW minus VW1, So hence force can be calculated. So work done per second is F into U. So therefore work done per second can be calculated. So per second, kinetic energy per second is half mass per second into V square. So hence 7850 is calculated Newton meter per second. Efficiency is work done per second by kinetic energy per second into 100, which comes to 37.5%. So moving to the next set of problems, where in all these cases, in the four problems, we discussed the direction of the jet leaving the vane was given like 120 degrees. So second case it was 90 degrees, third case it was 60 degrees, and fourth case also it was 60 degrees. And this is a particular case where the deflection angle will be given. So here the direction of the jet leaving the vane at the outlet has to be fixed by us. So that's how I will tell you how to fix up the velocity triangle. So after we solve a few steps, then you will be able to draw the velocity triangles. So here the jet of water having velocity 20 meter per second. So velocity of the vane is 10 meter per second, which is moving in the same direction as that of the jet. So inlet velocity triangle will be a straight line. Again, VR will be equal to V minus U. But the deflection angle is given 125 degrees. So diameter of the jet is 100 millimeters. We have to find force exerted, work done per second, and efficiency. So this is the jet direction as well as the vane directions are same. So that's the reason V and U directions will be same, and so VR will be V minus U. So now here this is the incoming direction, this is the outgoing direction. So this angle is given. So using this deflection angle we are able to calculate, because alpha is 0, theta is 0, and this angle becomes phi. So this angle and this angle are same. So now since 125 is known, so phi can be calculated, which is 180 minus 125, which comes to 55 degrees. So after knowing VR, we can calculate VR1. So because it's same, so VR1 cos phi can be calculated because we know the angle phi, we know VR1. So if by chance U is greater than VR1 cos phi, then this will cross this line. So it will be till here. If by chance U is less than VR1 cos phi, then U stops here only and the jet leaves like this. If U is greater than VR1 cos phi, then jet leaves like this. If U is equal to VR1 cos phi, then jet leaves at 90 degrees. So this is how we decide the velocity triangles at the outlet. Now in this case, VR can be calculated. So therefore, we can assume VR1 is equal to VR, which is 10 meter per second. So VR1 cos phi is calculated, which comes to 10 cos 55, which is 5.74 meter per second. So in this case, U is, which is 10, which is greater than VR. So U crosses this. So this is VR1 cos phi. So U is greater. So therefore, U is greater than VR1 cos phi. So the jet has to leave in this angle like this. So beta will be, so seeing this figure, beta is greater than 90 degrees. So now we know the angle phi. So therefore VW1 is U minus VR1 cos phi. So which gives here, so force can be calculated by this formula, minus sign because beta is greater than 90 degrees. So knowing rho, knowing A, knowing BR, knowing VW and BW1, the force can be calculated. Work done per second is F into U. So therefore work done per second can be calculated, and kinetic energy per second is half mass per second into V square. So that comes to 31400 Newton meter per second, and efficiency is output by input into 100, which comes to 39.35%. Taking the next problem, a jet of water of diameter 50 millimeters, where velocity of the jet is 20 meter per second. It strikes the curved vane, which is moving with velocity 8 meter per second. Now here the vane is symmetrical. Okay, so then theta will be equal to phi. Deflection angle is given. Okay, so you have to find the angle of the jet at the inlet, that is alpha. You have to find the absolute velocity of the jet at the outlet, which is V1, work done per second, and efficiency. So given the diameter, we can calculate the area. So velocity is known, so V is 20 meter per second, U is 8 meter per second, deflection angle is 120 degrees. So it's right different from the previous problem. Like Thus, in the previous problem, the jet and the vane were moving in the same direction. But in this case, so the angle alpha has to be determined. So the jet will be striking. By the time the jet strikes, the vane would have moved with velocity, and the jet strikes with velocity Vr, which is in the tangential direction. So therefore, here this is the incoming direction, this is the outgoing direction. So this deflection angle is given, which is 120 degree. Since it is a symmetrical vane, theta will be equal to phi. So therefore, theta plus phi is 60 degrees. Okay, theta plus phi is 60 degrees. So since theta is equal to phi, so 60 divided by 2, so that comes to 30 degrees. So now we know the value of theta. So here theta is known. So since theta is known, so this angle is 180 minus theta, which is 150 degrees. Now using, so take this angle as alpha, so and take this angle as alpha dash. Okay, so we are required to find the value alpha. So you can apply sine rule. So V by sine 150 is equal to U by sine alpha dash. So V is known, U is known, alpha dash can be calculated. So alpha plus alpha dash plus 150 is equal to 180 degrees. So therefore alpha can be calculated. After that, we can calculate VR. So VF will be V sine alpha, VW will be V cos alpha. So now you can apply tan 30 degrees is VF by VR. So VR can be calculated. That is what shown here. So therefore here by applying sine rule, so V by sine 150 should be equal to U by sine alpha dash. So alpha dash can be calculated, but alpha plus alpha dash plus 150 is 180 degree. So therefore alpha can be calculated as 18.46. So the angle with which the jet issues is known as alpha, which is calculated as 18.46. Now using this triangle, again knowing now alpha, so we can calculate Vf, which is V sine alpha, which comes to 6.33 meter per second. We can also calculate Vw, which is given by V cos alpha, which is 20 cos 18.46, it is 18.97 meter per second. So now using this triangle, sine theta is Vf by Vr, so Vr can be calculated as 12.66 meter per second. Now we can assume Vr1 is equal to Vr, which is equal to 12.66 meter per second. So how to plot the velocity triangles, the outlet velocity triangle? So this is VR1. So first to find out what is VR1 cos phi. So VR1, because knowing the value of VR1 and phi, so we can calculate as 10.96. But U is here in this case is less than VR1 cos phi. So since U is less than VR1 cos phi, so this is VR1 cos phi, this is U. So therefore, okay, so it stops, the jet leaves, okay, in this fashion. So beta will be less than 90 degrees. So in this case VW1 will be VR1 cos phi minus U, VR1 cos phi minus U. So that's what shown in the equation. So VR1 cos phi minus U is VW1, so hence VW1 can be calculated. So this is what's shown here. So force can be calculated because beta is less than 90 degrees, so plus sign is used. So therefore rho is 1000, area is known, so VR is known, so VW plus VW1. So force can be calculated, hence work done is force into velocity. So work done per second is calculated 4951.7 Newton meter per second. Kinetic energy again is half mass per second into V square, so which comes to 7850 Newton meter per second. Hence efficiency can be calculated as work done per second by kinetic energy per second into 100, which comes to 63.1%. So it is also asked to find out the absolute velocity. So since the beta here VR1 cos phi is known, so VR1 cos phi, okay, so we can calculate, and U is known, so VW1 is calculated as 0.96, which is VR1 cos phi minus U, and VF1 is nothing but VR1 sin phi. So using this triangle, so okay, so this is VR1, this is phi, so it has to be VR1 sin phi. So VR1 is known 12.66 into sin 30, which comes to 6.33 meter per second. Using this triangle, so we can calculate V1 is Pythagoras theorem, so root of VF1 square plus VW1 square. So that comes to 6.4. So this is the absolute velocity at the exit. So also we can calculate tan beta, which is VF1 by VW1. So beta can be calculated. If this is 81.4, so deducting from 180, we will get the angle with which the jet leaves. So the magnitude is 6.4 and in direction will be 98.6 with the direction of motion of the vane. Now we have a jet of velocity having velocity 45 meter per second which impinges on a series of vanes. So this is one particular case where I took series of vane, and all the cases I had taken one single vane. But there the series of vane are moving with 15 meter per second in the direction of motion of the vane. The direction of motion of the vane is inclined at 20 degrees to that of the jet. So alpha is 20 degrees. So the vane is shaped such that deflection angle is 120 degrees. So in this case, this is one case where I have taken relative velocity is VR1 is 0.9 times VR. Okay, so there is 10% loss. So we have to find the vane angles at inlet and outlet and work done per second and efficiency. So in this case, the same case here. So this is the incoming direction, outgoing direction. So 120 degrees. It's not a symmetrical vane, so alpha and theta are different. But here the angle alpha is given. So knowing angle alpha V, we can calculate VF, then we can calculate VW, and hence calculate theta. Because tan theta is VF by VW minus U. Knowing theta, so this total is 60 degrees. So knowing theta, phi can be calculated. So knowing phi, so now knowing VR1, so VR1 cos phi can be calculated. So now you can compare with U. So whether U is greater than VR1 cos phi, or U is less than VR1 cos phi, or U is equal to VR1 cos phi. So now knowing V and alpha, so we can calculate VF, which is V sin alpha, which is 45 into sin 20, which is 15.39 meter per second. So VW is V cos alpha, which is 45 into cos 20, which is 42.3 meter per second. So now using this triangle, tan theta is VF by VW minus U. So therefore theta can be calculated. So theta is 29.4. Also sin theta is VF by VR, so VR can be calculated 31.35. So we know that, so theta plus 5, okay, plus 120 is total 180 degrees. So knowing the angle theta, so we can calculate as phi, which comes to 30.6. So vane angle at inlet is calculated, vane angle at outlet is calculated. Now it is given that VR1 is 0.9 times VR, so therefore VR is known. Okay, so 0.9 times 31.35, which comes to 28.22. So we should know the how to draw the outlet velocity triangle. So therefore, so if this is VR1, so now this will be VR1 cos phi. So we know VR1, we know phi, so we can calculate VR1 cos phi, which comes to 24.29. But since U is 15 meter per second, which is less than VR1 cos phi, so therefore U is only this much. So therefore, so VW1 is U minus, VR1 cos phi minus U, VR1 cos phi minus U, so which is 9.29. Since beta is less than, from this diagram, beta is less than 90 degrees, so force can be calculated as rho A V. Why V here? Because it is a series of the entire mass of fluid is utilized in striking the vanes. In the single vane it is rho A B R, but in the series of vane it is rho A V into VW plus VW1. So work done per second can be calculated as rho A V into VW plus VW1 into U. Since the diameter of the jet is not given, so we calculate work done on the vane per unit weight of water, which is given by 1 by G VW plus VW1 into U. So that rho AV term gets cancelled out. So I'll tell you how it comes. So now knowing G, knowing VW, knowing VW1 and U, so work done per unit weight can be calculated, which is Newton meter per Newton. Kinetic energy, similar way, is half mass per second into V square. The same it comes to as V square by 2g, which is nothing but the velocity head. So 45 square divided by 2 into 9.81. So efficiency can be calculated as output by input, which comes to 76.4. So in this case, the diameter is not given. So you know that work done per second is rho AV into VW plus VW1 into U, which gives the unit as Newton meter per second. But since this is work done per second, we divide by weight here, since it is per unit weight. So weight per second, this is also per second, we make it as per second, but weight is specific weight into volume. per second. So volume per second is discharge. So the specific head is rho into G. So rho cancels out, Q cancels out. So we are left with 1 by G into BW plus VW1 into U. So that's the formula we used for work done per unit weight of water, which comes to Newton meter per Newton. Similarly, kinetic energy per second is also divided by weight per second. So therefore, half mass per second V square, half rho AV V square. So weight is the same thing, rho G into Q. So AV and Q cancels out, rho cancels out. So we are left with V square by 2G. And that's the reason why for input we have taken V square by 2G. For the output we take it as 1 by G VW plus or minus VW1 into U, depending upon whether it is plus or minus. Now this is a problem where we have taken a semicircular veins. In the semicircular veins, when you draw the tangents where alpha will be equal to 0, theta will be equal to 0, and similarly it comes out tangentially. So therefore the velocity of jet is given as v. So it strikes horizontally. The veins are moving with velocity 0.6 times v. So u is 0.6 times v. But relative velocity is reduced by 10%. So VR1 will be equal to 0.9 times VR. We have to show that efficiency is 91.2. So now it strikes with velocity. So by the time it strikes, the vein would have moved by u. So therefore, the velocity with which it strikes is VR. So therefore, VR is v minus u. So u is 0.6 times v. So it comes to 0.4 times v. So VR, when it comes out with velocity VR1. So therefore, it's 0.9 times VR. But VR is 0.4 times v. So that comes to 0.36 v. So now we know that force is so it is a series of veins. So rho AB is taken. Initial velocity is VR. Final velocity is minus of VR1. So minus of minus is plus. So therefore VR is 0.4 V. VR1 is 0.36 V. So therefore rho AB into 0.6 times V. Similarly, the work done per second is F into U. So multiplying by U as 0.6 times V. So we get work done per second. Kinetic energy per second is half rho mass per second into V square. So that's the same. So substitute work done per second and kinetic energy into 100. So this is substituted as work done per second, and this is substituted as kinetic energy per second. So rho AV cancels out, and you're left with 0.912 into 100, which comes to 91.2%. So these are the various problems that we discussed in the for the force exerted by the jet, which is striking tangentially at one of the tips. And we also discussed the velocity triangles, the inlet velocity triangles and the outlet velocity triangles, and the various problems. And this concept has to be understood very clearly so that it will be helpful for the turbines and the pumps. So hope you had a very nice session on velocity triangles, and you understood the concept of velocity triangles, which will be particularly useful for our next topics. So wait for my next video lecture, which will be on the turbines, where I'll be using the same concepts and will be similar type of problems will be solving, and we should know how the jet strikes at the inlet and how it comes out at the outlet. Thank you for here, so that we hope it will be helpful for you, and these lectures will be helpful for you. And keep studying, stay at home and be healthy. Thank you very much.